Okay, we kind of got this tougher train problem here. It's giving us the velocity of train A in this chart, and then it says find the average acceleration. Now you see the word average, you got to think slope. You're going to do the slope of the velocity between 8 and 2. So v of 8 minus v of 2 over 8 minus 2. It's just your slope, and then you're getting those numbers from the table. Like v of 8 is negative 120, v of 2 is 100, and you just do some arithmetic right there and then get that answer. And then since you're doing a slope of velocity, it's your acceleration units are always like that. So your velocity is meters per minute, position would be meters, acceleration meters per minute squared. Now letter C, it says, do the data in the table support the conclusion that train's A velocity is negative 100 meters per minute at some point? All right, they're asking, is the velocity ever going to be negative 100? You could probably use common sense and say, yeah, because, I mean, you got 40 and negative 120, and guess where negative 100 is at? Negative 100 is in between there. Now, if it says, does a data support stuff and support the conclusion? Must it be true? That's when they want to hear a theorem. You got to know your basic theorems. And so the theorems, if you needed to watch a little refresher video I did over the theorems in the blue packet, go ahead and do so. But that's your intermediate value theorem. Anytime you have a y value down here and a y value up here, and you're going to say, hey, it's somewhere in between, that's your intermediate value theorem. That's what's going on right there. So they mention a differentiable function. Remember, differentiable also means it's continuous. So I just wrote down, hey, it's continuous and differentiable. I think that you only need continuous for the intermediate value theorem to apply. And then I just wrote down like what we talked about, how we had a couple values right there, like v of 5 was 40, v of 8 was negative 120, and then negative 100 is in between those two values. So yes, it has to cross through negative 100 at some point because it's a continuous graph, and that's your intermediate value theorem. So you could just write IVT. That's a big one that they'll know what IVT is there, but you got to get that theorem in there when something must be true. All right, letter C was just kind of annoying because you had to do a bunch of stuff without the calculator there, and it gives us a giant paragraph we got to read, right? But it says at time t equals 2, the position is 300 meters east of origin station, and the train is moving to the east. Write an expression involving an integral that gives the position. So anytime it's talking about a position, you got to take into account the initial position. And then it says about using the trapezoidal sum, which we got to review that. I think we had that on either the 2003 or 2005 test, one of those. We got to do this trapezoidal stuff going on, all right? Now, so they want to know what the position is at 12. And then notice up here, it tells us the initial position at t equals 2 is 300, right? And so here's where I'm going to set this up. Let me put all my work up there for letter C. That's where we're at t equals 2. And so if you know where you're at 2, then we're talking seconds or minutes. But if you know where you're at 2 minutes, then you pick it up right where you left off, and you're supposed to go all the way to 12. So there's no point in putting a 0 to 12 right there, because this is where you're at after 2 minutes. And then you're going to start it at 2 minutes because you know where you're at 2 minutes, and then you're going to go to where you're supposed to go. So doing the initial position, and then when you integrate the velocity, it gets you the position function. This tells you how far you went in between 2 and 12. This tells you where you're at that 2. So this is what we got to get down. So you got to make sure you write that down. Anytime it says position, take into account that initial position. And then here's a deal when you have the integral. So they're always going to have us do something on the test where you need to approximate the integral. We don't have a function where we could just integrate it and plug in the 12 and plug in the 2. We need to estimate it using a Riemann sum or a trapezoidal sum. Now, Riemann sum was when we'll do the rectangles, and I showed you how to do that without doing the pictures at all. And then trapezoidal sum is where we got to draw on some trapezoids. Now, typically, if we could get one trapezoid, we don't have to draw all the trapezoids because it's a little bit tricky because some goes above, some goes below right there. So what I did is I went 2, 5, 8, 10. Let me just show you how to get like one trapezoid right here. Like if I use the one between 5 and 8, all right, you got the two bases, all right, you got the point 5 comma 40, and then you got 5, actually the one between, so ignore all, let me just kind of do this from scratch here. Let me kind of get rid of this real quick. All right. What was annoying to me, that's how my stuff wouldn't print the stuff out, man. It was just, I was like, that sucks. And then I just finally got the print properly and then was able to do that. But anyways, all right. So if you got the 0.2 comma 100 right here, and then you got the 0.5 comma 40 right there, and you're supposed to do a trapezoid, that's all you're doing. And they tell us this is 2 100, so that's one base, and this is 540, that's the other base, and then this is the height. So it's like a trapezoid laying on its side. And then so this height is equal to 3. So when I do my area formula for a trapezoid, we should have that memorized by now. It's in your blue packet. It's base 1 plus base 2 divided by 2 times it by the height. And then so I'm going to go 100 plus that 40 divided by 2, and then times that by 3. And then if you look at the actual chart here, you could kind of, once I get one, I don't draw the pictures for all of them usually. So the first one I did 100 plus the 40 divided by 2 times it by 3. And then the next one we're going to go 40 plus the negative 120 divided by 2 times it by the 3. And then the next one will go negative 120 plus the negative 150 divided by 2 times it by the 4. And that's how I'm getting those extra numbers right there. And so if they give you the negative values, use the negative values. But if it's like a total distance travel problem and you have absolute value bars right there, well, then you just use the positive numbers. Use the positive 120, the positive 120, and positive 150. And the annoying part of this part is like, we had to do this without the calculator. So I thought they could have made that a little bit like just quicker and easier on us. But I tried to show a couple different ways there. So just we'll look at my work there, make sense in your brain. At one time I pulled out a 1/2, try to do little bit by little bit. One time I just pulled out a 3/2 for these couple and pulled out a 2 or something. I don't know. But there's a couple ways, whatever works in your brain, figure that out. But then once you get the negative 450, do your plus 300, and then that gives you negative 150. And then what that means, negative 150, remember you're starting at the origin station, right? And then so negative 150 means you're going to go to the left, which means you're going to end up 150 meters west of that origin station. That's where your position is at after 12 minutes right there. All right, now I know you probably was wondering what the heck is going on in letter D, but I think once you see it, I think you realize it's a pretty straightforward related rate problem, okay? So it says we got a second train B that is this is for train A, the velocity. The velocity for train B is this equation right here. And it tells us that's 400 meters north of the station. And then it talks about the different train, and then it says find the rate in meters per minute at which the distance between train A and train B is changing at t equals 2. Now, when you set these up, this is a related rate problem. We've done these in the past. We've done harder ones than these in the past. But see, you're starting right here. So one train, they tell us is going east, right? That's like train A. I'm going to call that one X. And the other train is going north. That's train B. I'm going to call that Y. Now, remember on the related rate, if it's changing, you got to use variables for that. So that's an X, that's a Y. And it's talking about the distance between the two trains. So at some point, the train will stop here and stop here. If you pause it, this would be the distance between those two trains. So we got just a right triangle. We could probably use the Pythagorean theorem here. And you got to find out how fast that distance between the two trains is changing. In symbols, that means the ds dt when t is equal to 2. So you can use your Pythagorean theorem here. But see, now at t equals 2, we know a few things there. At t equals 2, they told us in part C that train A, the x was equal to 300. Also, they just told us right here at time t equals 2 that train B, which is the y, that's going to be 400. So when I go 2x dx dt, 2y dy dt equals 2x ds dt, the 2's carry down, that x is the 300, that y is the 400, and then remember what we could do there, we're pausing the problem at that instant, that's 300 and 400, you can use your Pythagorean theorem to figure out that's like a 3, 4, 5, 300, 400, 500 right triangle, so that s would be 500 right there. And then here's the deal though, I didn't know what the dx dt, the dy dt, or the ds dt were equal to. Now the ds dt was fine, I didn't know what that was because I was trying to figure that one out, so I just carried that one down. But we had to get numbers for the dx dt and the dy dt. Now the dx dt, that was like that was the velocity of train A. That was how fast train A is going at 2 minutes. And then that from our chart, that's going to be the 100. That's where I got my 100 right there. And then the dy dt is how fast the train B was going at 2 minutes. And then that's when I had to use this equation right here. I had to take the 2, plug it in right there, no calculator, plug it in right there, and I get that 125. And then I had everything I needed except for that DSDT. I canceled out the 2's right away. I was doing some old school multiply and divide and stuff like that. If the numbers ever get too complicated, you could just kind of leave it like if we just leave it as this divided by this, you know, they got to give us credit for that. They said they don't take off if you just leave it as a unsimplified fraction right there. So if the numbers ever get too high, just leave them alone. But if you can simplify, go ahead and do that. And then that's going to be meters per minute because it's how fast that this is changing. So there's a lot there, but make sure you go back and practice these things, all these problems on your own from scratch with the language, what you're supposed to do, and then just get some of those hard parts there because we gotta practice the tougher stuff, man, to make that, hopefully make it easier for us there. SpongeBob.